Yeah, thanks for inviting me to talk to this crowd and start communicating with new people that are interested in geothermal. It's great. Okay, so I guess we can go ahead and start in this first slide. So when I talk to general crowds like this, I usually like to start with an outline of what geothermal energy is and what it really looks like, because there's not a lot of public awareness of geothermal. So we're going to take a tour around Italy and California and Nevada before getting back to Washington. And I'll talk about some of the work I've been involved with and it's currently ongoing here in Washington State. And then talk about some of the limitations of the ordinary geothermal that's been developed for the last 100 years. And that brings us to how do we scale up? So engineered geothermal systems, and then how do we even scale that up further, which is super hot rock energy, which is what I've been focused on recently. And the way you get to super hot rock, or at least one way, is millimeter wave drilling, which is my company, the current company I'm at, Quaise Energy. And then I'll finish, get back to the Pacific Northwest and talk about New Berry Volcano, which is where we're going to be doing an early test of super hot rock energy. And I just like to start out by acknowledging that none of this work that I'm going to be presenting is solely mine. Worked on teams. Susan Petty is my mentor in geothermal. She's right there. She was my boss at Ultra. Worked with presenting some of Jonathan's work there with him. So it's a team effort. Make sure I acknowledge it. Okay, next. So just starting out at the very most general of what is geothermal energy. Really, it is heat below their surface. So that heat can be pretty low. So if we're talking about geothermal heat pumps, we're down at just kind of with the ambient temperature, but we're exchanging heat with the environment. So that counts as geothermal. Because a lot of people think that's all geothermal is. But of course, as you go hotter and hotter, you can get through direct use temperatures where it's direct use, hot springs and things like that. Boise, Idaho has a direct use program system where they're just taking hot water out of the ground and heating buildings. What I'm mostly going to talk about, though, is once you get above, say, 250 degrees Fahrenheit, where you start to get to temperatures where you can generate electricity. That's with binary geothermal power plants, which I'll explain. And then as you get hotter and hotter, actual steam, the hottest is really the super hot rock, which is kind of where I'm going, because there's just more and more energy, more and more efficiency as you get hotter and hotter. Next slide. Okay, so the advantages will start out with the kind of the conclusions, maybe. Why is geothermal so exciting, I guess? Part of it's dependable, 95% available, and, compared to solar and wind, they're down at, say, 25 to 40% of it. We're 95% availability. And can also operate flexibly or on demand. So that's more like a gas plant. And fill in the gaps caused by other renewables. No carbon emissions, high energy density. There's not a lot of surface development. All that development is really underground, especially if you can drill directionally, you can reduce the surface footprint. The fuel is free, or in one way you buy it up front, just like solar and wind, it's free. And it's low cost. And I'll provide you some background on this number of $100 megawatt hour or 5 cents to 10 cents a kilowatt hour. So where is geothermal now? It is global. It's a global resource. The U.S. has the most, about 3,900 megawatts. Other countries, in particular, around the Pacific Rim, so Indonesia, the Philippines, have quite high geothermal percentage of their generation. So over 10% of the electricity generated in Indonesia, Philippines, New Zealand, Kenya, and Iceland comes from geothermal. So those countries really have great resources and they're exporting. I guess that's all I want here. Next slide. It all started in Italy over 100 years ago in Tuscany. This is an area with a lot of steam and boron mining back in the day. First, this guy, Prince Giovanni Conti, in 1905, hooked a steam turbine up to a well, which is producing steam and generate power. And then eventually they built a real power plant in 1913. Until the 60s or 50s, when New Zealand started using geothermal power, Italy was the only place it was developed. And in fact, it was an important part of their electricity generation during World War II when they were cut off from oil and gas. Next. So if you go to Tuscany, which you should, for many other reasons, but this is what you'll see as far as the geothermal imprint on the land. So that's actually a cooling tower. And as I go, you'll see actually the cooling towers, kind of all you really see at geothermal power plants. It's the biggest part of the plant, typically. And that's basically because you've got a hot side of the turbine, the cold side. And so that's representing the cold side, causing condensation of the work. You can also see some pipelines across the landscape going to wells. But it's, they've been living with geothermal power right in these villages. Lauderdale was the name of this village for many years. Next. So what about the U.S.? This map shows basically it's a proxy for heat at depth. One thing you can see right away is that in the U.S., all the hot earth is in the western states. The black dots are hydrothermal sites with temperatures greater than 90 degrees C. So getting up to those temperatures where you can generate electricity. And there's fairly limited hot rock in the east, with some exceptions. And I'll talk about how we get that heat out later. But first, I'm just talking about conventional geothermal, where basically there's some sort of existing conventional system, a conventional existing circulation of fluids. And oftentimes there's some sort of surface expression. So next, I think it's, so the places that geothermal is installed right now, there's 49 power plants in California. That's really the majority, and that's in the U.S. There's two big fields, the geysers north of San Francisco and Salton Sea south of east of San Diego. And then quite a few power plants in Nevada that have been built out, because there's a lot of action in Nevada now. Utah has got 4 and growing, probably more than any other state, and I'll tell you why. And then just like 1 each in Alaska, New Mexico, Idaho, and Oregon. So it's pretty limited, and that's because we're following this method of finding surface expressions or just circulating on water and drilling near those. Like in the U.S., 3,900 megawatts. That's about 0.5% of U.S. energy use. And it is growing at maybe 10% a year, with a potential to double or triple it. Next. I think you skipped. Cool. There we go. So the geysers was the first place that geothermal power was generated in the U.S. Since starting in the 60s. There's 18 power plants. Again, that's what a power plant looks like in the geysers. That's the cooling tower. That's all steam vapor coming out of the cooling tower. So there's not any pollution there, it's just water. It's currently producing about 850 megawatts, which is enough for $1 million. It's been pretty really, I'm at school down in the Bay Area. I didn't know anything about the geysers. They had a really low profile for many years. I think in some ways they're increasing that profile, but it's not really known by that many people in the Bay Area that they get a lot of their power from the geysers. And just before we leave this slide, this is what a well pad looks like at the geysers, at least. There are 7 different wells. They're all drilled directionally out into the reservoir, so they're gathering heat and steam from a wide area. But pretty minimal footprint at the surface because of the direction drilling in the deep wells. Next. So what that looks like to surface, and this is actually one reason you can tell it's kind of a well probably drilled 20, 30 years ago, because it's leaking a little bit of steam there, and nothing too dangerous, but these wells have been around for a long time in many cases. And the geysers are a little bit unique in that it produces dry steam. So there's just not like a steam cap. It's like a natural gas, almost like you drill down into natural gas and you just produce the gas. The same thing here with steam in the geysers at a depth of, say, 8 to 12,000 feet below the surface. You can send that steam straight through a turbine, which is kind of the easiest you can get away with in geothermal. Usually, and I'll talk about next, you've got to do something else to out. Okay, so I'm going to switch to kind of the opposite end, which is where there's just liquid water in the subsurface. This is a project at Blue Mountain, Nevada, which is near Winnemucca. Here, the water comes out of the ground at around 320 degrees Fahrenheit. There are 7 producers, convection wells, and 5 injectors. And on this map, the producers are all connected here by the red pipeline. The hot water flows to the power plant here and then out to injectors connected by the blue pipelines. This is the site of Fervo's Project Red proof of concept. I'll talk about Fervo a little more, but this is where they first proved out the idea of their flavor of EGS. And it was recently acquired by Arm Technologies, which is the second biggest geothermal operator in the U.S. Next. So what that looks like in the field is now we have to have a pump because the water isn't flashing out of the well, or it's not steam like the geysers, and the water needs some help to get out of the ground. That's the electric motor there at the surface, driving the line shaft. There's a bump at, say, 1,800 feet down. This well flows over 2,000 gallons a minute, which is, just think of it as a big hot water well. But it's a really big well. You don't have very many water wells that produce that much. Next. And then once it flows out of the well, for example, right there, down the pipeline into the power plant. Again, cooling towers. This is a 50 megawatt plant, by the way. Next slide. But this is what the power plant that is used, or the power units are used for the Blue Mountain. And basically, there's a working fluid, in this case isopentane, which is boiled heat exchanger, where the geofluid loses heat to this working fluid. And then that vapor comes up through a turbine, spins a generator to then is condensed on this side. And this is where that cooling water, which are in the blue pipes, is used, is basically to create that condensation of the water. Next. Okay, so now we'll get back to Washington here a little bit. And some of the work I've been involved with is ongoing in Washington State. Notice we're up here in our left-hand corner, and there's a fair amount of heat we've got in the crust, but not a lot of hydrothermal sites, or none really of high enough temperature. That's partly because we get so much rain, just kind of sweeps away all the heat. But partially because there hasn't been as much exploration in some of the other states. So next, let's dive in and see what's going on in Washington State. We, of course, have the Cascade Range. We've got 5 young volcanoes. We have abundant seismicity. So we have these components of typical geothermal areas, like other places around the Pacific Rim. And in fact, back in the 80s, when a lot of geothermal exploration was being done around the country, the DNR drilled over 50 temperature gradient wells, did a lot of sampling, did actually quite a bit of work in Washington with kind of mixed results that are being updated now. But there just wasn't, we also have very cheap hydropower here, which has kept electricity prices, thankfully to our economy, low, and that suppressed things as well. The project that I was involved with back 2015, 2020, something called a play fairway analysis, basically where you looking for association of permeability and heat to create favorable areas for geothermal production. So this was a DOE-funded project with the Department of Natural Resources, and then Ultra Energy was the corporate sponsor. In the first phase, we compiled data, gap analysis in order to suggest additional data collection. In the second phase, we collected that data. And then in the third phase, we drilled temperature corals. So the 3 sites that we focused on were Wind River Valley, down right off Columbia, down by Carson, Mount St. Helens, and then Mount Baker. And I'm mostly going to talk about Mount Baker now because that's where follow-up work's being done. It's kind of where we got the most exciting results. These are still areas down here that are probably worth looking at again. And then you can see actually on this map that the yellow is areas with some resource potential. All those areas ought to be looked at further as well. Those are all areas with potential resource. Next. So some of the data we collected, and there's probably not many geoscientists in here that will understand these different data sets we collected, but these are the kind of things that are just typically done for geothermal exploration. It's also used for, a lot of these are used for mining exploration and oil and gas exploration as well. And also academic research. So gravity, basically the density of rocks, magnetics, whether the rocks are magnetic or not, straight the magnetism. LiDAR to look for surface faulting. So basically that's very detailed topographic maps. With cross sections. Magnetotellurics is a way of measuring resistivity of the ground. We also did some dating and geologic mapping. So we collected all this data and our 3 different sites in phase 2. Next. And then I'll put this data through a model to determine favorability. And basically there's 3 types of favorability when you think about geothermal. You have to have a heat source. So you have to have a heat potential. Maybe it's magmatic systems. Maybe it's fluid flow through fractures of some sort, or will be those things. And then we have to have fractures which are full of fluids. That's our resource, basically. We're almost never in rocks which have matrix permeability like a sandstone. We're almost always in rocks that are broken and fractured, and that's where the fluid sits. And then the fluid also has have to have a way to move around, basically move in those fractures. So we developed a methodology. This is one area that machine learning, AI could probably really help crunch this data better than we did. This is a few years ago. This is kind of based on expert opinions more than AI. So this is an area, how do you take all this data and crunch it down and figure out where a favorite spot is? Next. Here's an example of one of those favorability maps of the Baker area. This is, if you've been up there, this is Baker Lake. There's a hot springs called Baker Hot Springs right up there, and then the mountain is up here. So we're not on Mount Baker at all, actually. We're down slope quite a bit from Mount Baker, near Baker Lake. But there's still the heat from that volcano underneath our feet here. And these are areas where we felt that that fluid could find a way to the near surface. We knew it was at the surface because there's a hot spring. So we picked a drilling location based on this map right here. We brought a core rig up, drilled, and got this core here. It tells us what the lithology, the alteration is. And we got image log. Basically that's dropping a like camera-like device down the hole. And there's actually that's a fracture. That's the kind of fracture you look for in conventional geothermal. That would be flow rate fluid possible. This is too shallow. This is a 400 meter hole, so it's not that hot actually. We reached a maximum temperature of 34 degrees C. But what we did see is a 64 degrees C per kilometer gradient. Keep this, I already talked a lot more about gradients as we go. And that's a pretty good gradient. That's actually 2 to 3 times what you would expect if you weren't next to a volcano. And that is probably good enough for a geothermal resource in this area. Next. So the follow-up work that's being done by Hot Rock Energy Research Organization and Susan, Petty, and Jill Watts are in the audience. You can get them up for the questions afterwards if you want. Is funded by the Washington Department of Commerce, and I think there's someone from Commerce here too, and managed by the Nooksack Tribe and Whatcom County POD. And this is hot off the press work, which is we look at this old area and say, well, that's our potential hydrothermal resource area. We know something about the measured temperature from our borehole or core hole. We can do something called the power density method, which is basically looking at the area we have here, making some assumptions about doubt, comparing it to other global projects. We can then kind of feed that all into a Monte Carlo simulation method and see, how often or what sort of geothermal power is possible given the data we know right now. And so the reason Monte Carlo basically is a way to create thousands of tens of thousands of realizations of your data and see, what your results are. So this histogram just shows that Monte Carlo output. They found that the most likely geothermal output would be 21 megawatts with a pretty wide range of, say, 10 to 30 megawatts. That's pretty good. That would be a great geothermal power plant. But it's not clear that's technically feasible, economically feasible at this stage. Is it worth, the investment to put in a 30 megawatt power plant? And utilities like big. They don't really want these small projects. They want 500 megawatts. So what we go to next is, okay, how do we make it big? How can we scale up geothermal? So as I said, geothermal is kind of limited to these areas around the Pacific Rim, areas of active tectonics. And this is where we're at now. Maybe we can grow that 3 times. And how do we grow it, 10, 100 times? And how do we grow it outside of these areas? Next. Okay, so that solution is engineered geothermal systems. And it's also been called geothermal. And the idea here is all we got to do is find hot rock. And so hot rock we can actually find everywhere. It's always below us. It's just a matter of how deep we can go. And so we'll go for EGS. The idea is to go in areas where that hot rock is shallower to start. But eventually, and this is where my company Quaise comes in, we want to go any. And the steps to create an EGS system is drill an injection well, blue line here, install a microseismic array. Basically, you're looking for earthquakes, and because what we're gonna do is create micro earthquakes at depth to connect these wells up. When you break rock, shear rock, you create micro earthquakes, and you can detect that. Once you know where this system is, you can drill a production well into it and then circulate water through the system and bring hot water up these streams. So this is the engineer part is this reservoir, and I'm going to talk the next slide quite a bit more about this. There's a lot of ways and concepts of how to get the heat out of the ground. Basically, you're creating a heat exchanger at depth. And I don't have time to go far into any of these, but the basic concept is you're creating surface area down to hole, whether it be with just drilling, which is what closed loop solutions are, whether you're counting on existing fractures, you're just trying to improve those fractures. That's what we sometimes call enhanced geothermal. Susan and I did a project at Newberry Volcano using this methodology back, I guess about 10 years ago. You can create planar fractures with hydraulic fracturing. And I'm going to basically focus on this right now because it's right now kind of the flavor, I guess, of the decade right now for geothermal. And they're making a lot of progress in Utah. But there's other ways to do this too. You can try to rely more on the natural fracture system, which is this hybrid fracture network. Or if you get hot enough, thermal fracture becomes more and more important. You may just be able to add cool water to the volume and connect up because of thermal fracturing. And that's super hot geothermal. And that's actually what we know happens in some of these geothermal fields. So what are some of the key technologies we need for EGS? One is comes straight out of oil and gas, which is PDC bits and directional drilling. What this allows us to maximize the surface area for heat extraction downhole, minimize any surface impacts because we're drilling directionally from single pads, and shorten the drilling times because we time is money, and we can basically save money by drilling fast. Polycrystalline diamond compact bits, which is what that is have been around for a while, but have just recently gained a lot of use in geothermal. Mud motors, rotary steerable, that's what allows us to steer. And then the monitoring while drilling, it provides us the guidance to know where we're going. Directional drilling, and PDC bits has been very successful at projects in Nevada and successfully deployed EGS systems. And the prices have come way down, which is great. Next. The other technology from also borrowed from oil and gas fracking is hydraulic fracturing and zonal isolation. Basically, what we want to do is connect two wells or multiple wells in the subsurface along fractures. And that's what this model is showing. Of course, we can never see it, right? We can only model it. And the way we do that is with pump trucks to hydraulically fracture. There's a pump fleet in at Blue Mountain. Zonal isolation, which just means we want to create multiple fractures, and we have to isolate small areas between a plug and the surface, and we perforate holes through casing. And that allows us to drive these fractures out from the well using our pumps. And then we have to have proppants to hold those fractures. So this is fracking. To me, it leaves out the bad things about fracking, which is the toxic materials that are pouring out of ground, which is oil and gas. Those are toxins. And it uses the good parts. So this is just injecting water, sand, maybe some chemicals that allow that sand to be held in place. Next. So the company that's brought this all together is Quaise Energy. They have a project in Utah. They did a project in Nevada at Cape Red. They're doing this in Utah now. They've drilled and simulated about 24 wells, as near as I can tell. And they're building a 100 megawatt power plant right now. That's this power plant. Again, that's the cooling towers. And then they'll bring the binary power plant part and plate next door. There's a drill rig too. They're continuing to drill. What it looks like underground is this is a cross section, so slicing into here. As these wells go down about 9,000 feet, and then turn horizontally direction, like I said, and go about 5,000 feet at a temperature of 200 degrees C, 400 degrees South. This also happens to be the site of a conventional geothermal power plant called Blundell. So they have a well nearby, and then also a research site called Forge. So there's a lot going on in this valley. Next. So what's the electricity going to cost for Fervo? Of course, Fervo doesn't tell anyone. They give some hints. But Jonathan's been doing some modeling using a computer code developed in Intel called GeoFires. He just presented this a month ago for the Pacific Northwest RIG. And basically, he created a Fervo Cape Station-like model and calibrated his model to that. And for Cape Station, determined the cost of levelized cost of electricity of about $75 a megawatt. And then he basically adjusted it for state maps and geology for Washington State and came up with pretty much the same number. And here's just a shock. Washington State acts slower than Utah, so we actually a little lower cost for the maps. And then he applied that to the other geothermal prospect areas in Washington that I was telling you about. So Red River Valley, some different thermal gradients. Mount Baker, remember we measured 64 Celsius degrees C per kilometer gradient. That ends up with about $77 a megawatt hour. If we assume that the Fervo model and we can just move it, plop it down into Washington. There's actually not room enough at Mount Baker probably for the 500 megawatts that this project does, 60 doublets. But that's the idea is how would you transfer the Fervo's learnings to Washington State. We drilled a very cold well at Mount Collins. It was only 15 degrees C per kilometer. Good question.
Yeah, just is this what they would be providing as a generation cost onto the grid, or is this like sort of pre-profit or post-profit?
Pre-profit for sure. So it's
Cost, not price. Cost, not price.
Cost and price.
It's cost, not price, exactly. So we don't know what they're selling for. We think they're selling for over $100 a megawatt hour on some of their initial projects at least.
So, thanks.
And this is levelized cost of electricity. It's tricky, and I'll let you talk about this as we go. But it's used for comparing, coal electricity generation. So that's kind of why we use it. I guess I missed. Oh, I was just gonna say, we drilled a very cold well at St. Helens. In one spot, it was only 15 degrees C per kilometer, so that would be far too cold to be economic. But I'm glad I tried that model. But anyway, so now it's probably much higher than that, or maybe negative IRR on that project. Next. Okay, yeah. So how does that compare? This just showing you can look up LCOE, this graph I found at the National Public Utilities Council. Highly compare. So first, I want to say that some of these LCOEs are for intermittent sources. And so they're pretty low for onshore wind and solar. That's because they're not always on, right? Once you add batteries or storage into any of those intermittents, they come down that kind of cascade downward. You get to be quite a bit more expensive. But geothermal is right in the mix. So $61 to $102 a megawatt hour is what these guys calculated. Now that's not AGS, that's existing geothermal. And so it is cost competitive with everything really, especially if you're looking at storage for the intermittent geothermals. It's actually cost competitive with gas combined cycle, gas peaking. Down here, we're actually probably better. Because gas peaking, which is kind of how a lot of the gas plants are being built, much less efficient than just a baseload gas. So as Jonathan showed, EGS and 200C is theoretically competitive, at least a yellow dot. But I I'm still myself skeptical about some of these numbers for EGS. So I want to do better, reduce cost even more and risk. And so we can do that by going even higher. So next, we're going to transition to what I've been working on really the last 7 years in my current company, Quaise Energy is focused on. So, and that is super hot rock energy. And so why super hot? Basically, what is super hot rock? First, it's rock formation with a temperature greater than 375 degrees C, which is the critical point of water. It has very high enthalpy, which is just a measure of energy content. And we can think about drilling wells which are 30 megawatts per production. I should have said back when I was on Fervo or any other plants, they're around 10 megawatts per well max. So we're talking about probably 3 times other production wells for production. So 3 times, and you get there because you've got 3 times the heat content, 3 times the energy conversion, because as you get hotter, it's easier to, basically it's a Carnot cycle. It's more efficient to generate electricity from higher temperatures and reduce levelized cost of electricity. And we can start to talk about $45 a megawatt hour, which is this DOE Earthshot LC. That's an enthalpy diagram, which I will bore you. Next. So fortunately, Jonathan did this sort of analysis as well in his recent work. And by the way, if you go to his website, you can download a PDF, which he's just published on his website, Scientific Web Services. So he did 3 cases, basically still using that Fervo model, basically, and where he used low to medium temperatures, so 200 to 290, hot 300 to 73, and super hot, which is about the brick, and found that you get 25% lower cost of electricity in this model, so getting down to $50 a megawatt hour with super hot, lower capex. And I think, to me, most interesting is far fewer wells. So that 500 megawatt power project required 53 production wells. So these wells come in doublets. So there's 53 production wells and 53 injection wells. So 106 wells in this particular case. But now, if we're doing super hot, we can do it all with 15 doublets. So that's really where the cost savings comes in, because wells cost a lot. Next. Just another version of the same thing, megawatts per well versus reservoir temperature. And this, I'm also showing flow rate here, but and most of these projects, we assume, will flow right around 80 kilograms per second. So that the low to medium case, and this is basically Fervo wells. Ormat is a company that now owns Blue Mountain, I said, and basically they're down. Their wells are probably 5 megawatts per well. Fervo's shooting for around 10 megawatts per well. If we can go hot, we can get to 20 megawatts per well. If we go super hot, we're up at, say, 30 megawatts.
Do you have a new law between decline curves across?
Yeah, so I'm not talking about decline curves here, but yeah, they're all the wells are you're mining heat, you're pulling heat out of the rock, right? So they all decline. All these EGS projects decline. It's more about surface area than temperature. So, and that's kind of the one of those slides I showed is if you can maximize your surface area, you can reduce your decline. Never to zero probably, but we're talking about maybe 2 degrees per year, maybe acceptable. Decline curves are something that people go pretty close to their chest because they don't really want to know what it is. Fair goes the same way. The rumors are they're not seeing any decline yet, but they haven't really been operating. It's all very mild. Another question.
What would you say, maybe 2 degrees per year? Like, what kind of capacity factor you assume to the power plant? Could you reduce that by, running it, less frequently when, at times when it's time to backfill, wind and solar?
You can do all that. Geothermal, usually we just sell as much as you can. Just remember, you pre-bought all this fuel, spent a lot of money. You've got a loan based on your maximum generation. So if someone's going to pay you to go idle, you could do it. But you're going to convince the utilities to do that. And you would save a little, you might save a little heat in place. And one way to do it maybe is you start at a lower flow rate and then increase your flow rate, because you kind of want to levelize your production over time rather than have it decline over time. The other way to do it, talking about decline curves, is you drill makeup wells. So if you're constantly drilling, and if you look at the gas industry, they're always drilling wells, right? And that's one way they bring their costs down, is they never let the rig leave. The rig is always there drilling. You're always drilling makeup wells. You can fight your decline curves. Next, Susan.
So on the LCOE slide that you had, I mean, some of these costs, even at current state, or I think you had 8.5 cents is pretty, or 7.5 cents is pretty good. What would you say are if any, are the major engineering challenges that still have to be solved to actually make this much more prevalent?
Well, it's consistent. I think we just got to do it. I don't know if there are engineering, right? I mean, this is being done right now in Utah. Right? So I think it remains to be seen how long and this is why the decline curve question was a good one. How long will it be sustainable? There's definitely engineering about how do we plug up cold paths. If you start to see a well decline too quickly, how do we engineer that? But on the start, we've kind of done it. Although, Thermo hasn't really delivered any electrodes yet, so we're hoping they'll do it. Yeah. So, but let me get to super hot. I think super hot is one way to do that. Just go hotter and hotter. Once you go hotter, you're reducing your risks. You're improving it.
Does that LCOE have some specific time frame that you assume?
Actually, John.
Yeah, so that's over a 30-year project life.
So he included makeup wells in his LCOE.
And redrilling every 10 years. So it accounts for the drawdown and the redrilling costs from that.
Next. Okay, so I've convinced myself that I've been working on super hot and now Quaise is that really the pathway to cost competitive scalable geothermal anywhere is super hot or going. Fervo's definitely got a niche. They're working on it. I think hotter is better. And super hot resource is pretty available at depths of 7 to 15 kilometers in the Western U.S. We have a two-prong approach at Quaise, which is we're going to do super high EGS first in areas where you don't have to go so deep. So that's what we call tier 1 sites. These are magmatic sites where our temperature targets 300 to 425, that hot to super hot that Jonathan modeled. We can reach those depths at places like Newberry Volcano, which is this picture here at 3 to 5 kilometers. We can do this with conventional drilling today, and we're going to do that. So, then the next stage, once we want to try to start expanding to more areas, we can target depths of 10 kilometers. This is going to require some new drilling technologies, which I'm going to talk about in a second. So advanced drilling, low-cost drilling method to reach high temperatures. Eventually, we want to go to places with very low gradients. That might be when you start going out east. Some of these areas, Pennsylvania is where there's a lot of demand right now for electricity. They're probably going to be doing gas plants right now for the data centers are real. But, there's a lot of interest in bringing geothermal to Pennsylvania. And the only way really to do that is with some advanced drilling. You can't do that with PDC beds and conventional approach that Fervo's. Fervo's pretty focused on this area. We're going to start here. Quaise is going to move across the country. Next. So the way we're going to do that is with something called millimeter wave drilling. It includes a gyrotron, which is the energy source that creates these millimeter wave. Just think of your microwave on steroids. It's also gyrotrons are used for fusion research. So the Tomahawk in Europe is using 24 gyrotrons to contain plasma for fusion research. Requires a purge gas. We're going to pump gas down this hole. We're going to have the millimeter wave is going to go down a waveguide. We're going to have it's going to dissolve vaporized rock, and then using a purge gas, blow that rock back out to the surface. So that's how we're going to drill. Here's an example just in the lab. I'll show you some more examples. Next slide. So we've hooked this system up, the entire kit, to a full-size triple rig at a yard in Houston with our partner Neighbors Drilling. Gyrotrons in that box, so it's not huge really. We've got a power source, chillers. The waveguide goes up and it comes down and down a pre-made hole in a way. We started just with a small gyrotron, 70 kilowatts. We're moving up to a megawatt next. We started with a 4-inch hole. We're moving up to 8.5 inch holes. So we're planning a field project in 2028. And we're also working out how to drill direction with the Next. So what we've done so far, we've done things in the lab. We've drilled a 3-meter hole just outside our yard using 100 kilowatt gyrotron. And just recently, we moved to a field site here at a place called Werewolf Falls. And just this week, we reached a depth of 118 meters drilling with our millimeter wave. So it's working in the real world today. So there's still a lot of work to drill 10 times that, to drill 10,000 meters or even 1,000 meters. But we're on schedule to drill 1,000 meters next year. So it's pretty exciting. But, no one's really invented a new way to drill for a while. And this is it. And this is what's going to, you think, allow us to unlock geothermal around the world. Next. So just why is it better? Conventional drilling, even if drill bits last a long time, they're getting better and better. You're going to have, whenever you change a drill bit, you have to trip entirely on the hole and place that bit and go back in. So as you get deeper and deeper, say below 4,000 meters, the cost of conventional drilling, these curves here are just different examples, it's going to start going up exponentially because drill bit changes, anything changing out holes increase those costs. Whereas with our energy system, there's nothing downhole. Basically, you can drill with linear and increasing costs. At least is our theory right now. We don't have any reason not to do that. So we can run our gyrotrons with 4 megawatt generators, pretty similar energy costs to conventional rigs. We can optimize and drill hybrid drilling, so drill conventionally. And now Fervo has shown us that we can drill pretty cheaply. These X's are where Fervo's been recently. They drilled about 4,000 meters for $5 million. We can just do the same thing, drill that depth using conventional drilling, and then millimeter wave from there on to get deeper. And start talking about 7.5 kilometers, 10 kilometers. Next. So first we have to figure out how to do super hot EGS. There's a Newberry volcano south of Bend, Oregon. It's one of the largest volcanoes in the Cascades. It's a big shield-shaped bi-global composition volcano, about 600,000 years old. It has magma. It just erupted last 1,300 years ago. That is the big obsidian flow. This is another place you need to go. Check this out. This was an important obsidian source for Native Americans. You can walk right up onto it. It's pretty neat. Newberry has a national monument that protects this obsidian flow and kind of this entire caldera. But there's a lot of leases outside of the And this was the site of 2 demonstration projects for each of these. Next. So very high gradient, 100 degrees C per kilometer. Remember back, Mount Baker was 60 degrees per kilometer. This is a lot higher than that because it's a much bigger volcano, bigger magma chamber. It's well characterized by 50 years of exploration here. There's been demonstrations already. It also has there's local data centers nearby for an off-taker, and then connection to Bonneville Towers transmission line, which already connects Washington, California. Runs the valley right here. Next. So basically, this just shows a thermal model. As you go deeper, it gets hotter at Newberry. We're just aiming for the 400 degrees C depths at the moment. The wells have already hit 300 degrees C. So we just have to go a little bit deeper than the existing wells there. And that large volume is our reservoir between 450 and 300 degrees C. So we should can reach with, say, 5 kilometer deep or 15,000 foot deep wells. And the reason it's hot is because there's just been this intrusions underneath this volcano for the last 600,000 years. There's probably easily a gigawatt of electricity, of heat underneath this volcano. So we're planning to drill some exploration wells there soon. Next. Oh, there's our well. So the goals of our first project are 20 megawatts. We call it the nth of a kind because it's actually not our first project, our nth of a kind project. So once we get beyond first of a kind, wells which produce 20 to 30 megawatts per well, high enthalpy, that have a sustainable fuel operations for 15 years or more. And, wake up wells, are going to be part of that fuel operations. Levelized costs less than $60 a megawatt, and low risk of induced seismicity. I didn't talk much about that, but EGS has had some problems with that in the past. We know how to mitigate that, and we think it'll be less in higher temperatures. Next. So basically, deeper, hotter is kind of the thesis of Quaise leads the way to a new energy frontier. We can start in the operating areas here, which already has geothermal. We can move across the country. We can actually reach, let's see, 20 kilometers. We can reach 300 degrees C, pretty much in 95% of the country. So if that's our we can start to drill that, we really have unlocked a new type. And just the final thing is, this is showing coal plants where they currently exist. So we now start thinking about geothermal taking over where coal plants currently exist and leveraging that infrastructure that we're hoping will be stranded because the coal plants are shutting down. And next. So yeah, that's it. I went through a whole lot of stuff. So a reminder what I went through in case you want to ask questions about any of those items.